So welcome everybody. The topic for today is SLT and alignment. And I want to start by explaining a bit about what this potential application area for SLT is. So alignment or AI alignment is a subset of AI safety. There are lots of resources online that you can find that introduce the area, but I think the most succinct explanation is actually in a book from 1964 by Norbert Wiener, and I'm going to read a short story from there to begin this discussion. So you might be familiar with this story. It's by W. Jacobs. It's called The Monkey's Paw. In this tale, an English working family is sitting down to dinner in its kitchen. The son leaves to work at a factory, and the old parents listen to the tales of their guest, a sergeant major back from service in the Indian Army. He tells them of Indian magic and shows them a dried monkey's paw, which he tells them is a talisman which has been endowed by an Indian holy man with the virtue of giving 3 wishes to each of the successive owners. This, he says, was to prove the folly of defying fate. He says that he does not know what were the first 2 wishes of the first owner, but that the last one was for death. He himself was the second owner, but his experiences were too terrible to relate. He is about to cast the paw on the coal fire when his host retrieves it, and despite all the sergeant major can do, wishes for £200. Shortly thereafter there is a knock at the door. A very solemn gentleman is there from the company which has employed his son. As gently as he can, he breaks the news that the son has been killed in an accident at the factory. Without recognizing any responsibility in the matter, the company offers its sympathy and £200 as a solitium? Don't actually know this word. Solace, I suppose. The parents are distracted, and at the mother's suggestion they wish the son back again. By now it's dark without, a dark windy night. Again there is a knocking at the door. Somehow the parents know that it is their son, but not in the flesh. The story ends with a third wish, that the ghost should go away. The theme of all these tales, I'm continuing, this is Vina now. The theme of all these tales is the danger of magic. This seems to lie in the fact that the operation of magic is singularly literal-minded, and that if it grants you anything at all, it grants what you ask for, not what you should have asked for, or what you intended. If you ask for £200 and do not express the condition that you do not wish it at the cost of the life of your son, £200 you will get, whether your son lives or dies. The magic of automation, and in particular the magic of an automatization in which the devices learn, may be expected to be similarly literal-minded. If you are playing a game according to certain rules, and you set the playing machine to play for victory, you will get victory if you get anything at all, and the machine will not pay the slightest attention to any consideration except victory according to the rules. This is around page 60, by the way, of the book God and Gollum. Okay, so I'm going to continue to read a few pages later. While it is always possible to ask for something other than we really want, this possibility is most serious when the process by which we are to obtain our wish is indirect, and the degree to which we have obtained our wish is not clear until the very end. Usually we realize our wishes, insofar as we do actually realize them, by a feedback process, in which we compare the degree of attainment of intermediate goals with our anticipation of them. In this process, the feedback goes through us, and we can turn back before it is too late. If the feedback is built into a machine that cannot be inspected until the final goal is attained, the possibilities for catastrophe are greatly increased. I should very much hate to ride on the first trial of an automobile regulated by photoelectric feedback devices, unless there were somewhere a handle by which I could take over control if I find myself driving smack into a tree. Okay, so he's talking about a Tesla there. Okay, so I think that's very well put. I'm going to highlight some of the ideas brought up in that and use that to kick off a broader discussion of AI alignment. So let's see. There was an emphasis there on feedback, right? So usually we realize our wishes. wishes. By a process of feedback. Now, that's referring to the fact that we don't actually know how to specify what we want. That's clear in the story, right? Partly we can specify some things we want, but there's all sorts of unspoken conditions or side effects we wish to exclude, which are hard to specify because in part they're infinite, right? And it's partly by examining the process that's realizing our goals and noticing when things are getting out of control that we're able to actually ultimately specify what we want. If the feedback is built into a machine that cannot be inspected, and this here is what we're going to focus on. So if the feedback is built into a machine that cannot be inspected until the final goal, I guess we would call that a black box. The possibilities for catastrophe are greatly increased. Now, the monkey's paw example and the mention of magic is meant to put into place the idea that the system we're interacting with, whether it's the monkey's paw or, in our context, an advanced AI system, is highly competent, right? So it's capable of transforming the world in significant ways. And that means that if we don't understand how it's working or what it's doing, we can't meaningfully intervene or stop things from, even if we specify an end goal, which is something we want, we may not get exactly what we want. Okay. There's some comments later. Maybe I'll see if there's anything else I want to read from there. Feel free to, throughout this whole thing, I'm just going to read a bunch of passages to start. I'll show you some various things from different papers and then talk about this alignment plan that's on the MetaUni page. But this is meant to be an invitation for questions and discussion as much as anything. Yeah, so maybe I'll keep reading for just a bit. The gadget-minded people often have the illusion that a highly automatized world will make smaller claims on human ingenuity than does the present one, and will take over from us our need for difficult thinking, as a Roman slave who was also a Greek philosopher might have done for his master. This is palpably false. A goal-seeking mechanism will not necessarily seek our goals unless we design it for that purpose, and in that designing, we must foresee all steps of the process. For which it is designed. Instead of exercising a tentative foresight which goes up to a certain point and can be continued from that point on as new difficulties arise. The penalties for errors of foresight great as they are now, will be enormously increased. as automatization comes into its full use. I can't think of a better way to put it than that. So, we should aim for systems that we can inspect and understand, so as to not make errors of foresight and end up with unanticipated and undesired consequences. Okay, so what is AI alignment? There are many things that need to be gotten right in order for advanced AI systems to be safe and compatible with human flourishing. One of the things that needs to go right is we need to be able to get what we want. Now, note this isn't necessarily about figuring out how the most enlightened human would behave and then getting an AI to do that. Right? This is the simpler question of just getting it to do anything at all. So Eliezer Yudkowsky has a good example of we don't even know how to get an AI to make a strawberry and do nothing else. The idea being that it's very difficult to make a strawberry if you're doing molecular manufacturing or something, but you could substitute for that any sufficiently advanced task which requires inventing new science and therefore extreme capability, but is bounded in the sense that it does that and doesn't do something else. And this is basically exactly the same as getting that 200 pounds.
Dan?
Yeah.
I'm not sure if it matters for the present discussion, but I think Eliezer's example is not just to make a strawberry, but to make a molecularly identical copy of an existing strawberry. So it's like you give it a strawberry and you say, can it make next to that a molecularly identical copy? And so that's very well specified, and we don't know how to get it to do that without destroying the world.
Yeah, thanks. That's right. Yeah, I'd forgotten that it was a copying. Okay. So one could say much more on what alignment is and what the various approaches are. I think that's not the talk I want to give today. You can find pretty good resources for that on the Alignment Forum. The AI Safety Seminar webpage has lots of references on it. So I think I'll just defer a further discussion of the fields to those resources. So there are many things that we have to understand in order to solve the problem of getting an advanced AI system, say more capable than a human being, to do what we want. Understanding what's happening inside such a system may be neither necessary nor sufficient. We may somehow figure out a way of aligning very advanced AI systems while they remain completely black boxes. I think I don't see a lot of plausible approaches that completely have them as black boxes. So I'll discuss a little bit later some of the alignment work that's happening at DeepMind, and that hinges very closely on progress in understanding inspection of these machines, or interpretability as it's called. Similar programs going on at OpenAI and Anthropic and elsewhere also involve assuming that we're going to make significant progress on that, and that's the area of alignment that I'm going to talk about mostly today. Yeah, Matt comments, humans are essentially black boxes, and it's instructive to think about how we control humans that we don't necessarily trust, and it hinges largely on bounds on their capabilities. And I suppose the reason I see that as being not a sufficient attitude towards controlling AI systems is that we just don't have any such guarantees or bounds. If they were human level roughly, we could maybe apply similar techniques as we do to cooperating with humans. Okay. So it's natural when you first encounter this topic to maybe be a bit skeptical that it's a serious problem. I don't want to spend too long on that, but I'll just give the two high-level reasons I find most convincing. So they're more or less just like pointing out what I would say are fallacies based on intuitions you might have. And I think the overriding point is this is a new problem. I think it's common when you encounter a problem to reason by analogy, right? To seek out historical analogues and to gauge how dangerous you think a situation is or how hard it will be to solve something by comparing it to something that you understand already, which seems similar. But of course, every now and then we encounter situations that are really genuinely different to anything we've encountered before. And I think this seems to be one of them for the reasons I just described, right? It's not guaranteed we'll be able to build AI systems much more capable than humans, but there seems to me and to many people to be no fundamental obstacle, and we seem not to be extremely far away from it. So presuming that's going to happen, if those systems exist, then there really is no reason, I think, to think that the problem of controlling them or understanding them is analogous to anything else that we've done. So in particular, a lot of people have this idea that maybe as systems become smarter and more aware of context and more knowledgeable, that they will be wiser and more benevolent somehow automatically. This is the fact that these two things might be different is a corollary, you might say, of what's called the orthogonality thesis. So the orthogonality thesis is just pointing out that it seems highly possible that you can have very advanced intelligence deployed to arbitrary goals. So something stupid, seemingly stupid, like making paper clips, could be the designed goal of an extremely advanced intelligence, and there wouldn't be a necessary fundamental reason for those two to conflict. And in the same vein, there's no reason to think that just making systems smarter will automatically make them more compatible with human flourishing because they'll be benevolent. Debating that could take up hours and hours and hours, but that's at least, I think, clear. So that's point one. The second point that I find convincing is the idea of instrumental convergence. Again, I won't spell out the whole idea. You can read about it in various places. But as a subset of instrumental convergence is the idea that agents which are designed, well, let's just say AI systems, that are given fairly generic goals, for example, make human life on Earth awesome, will, by pursuing those goals, instantiate proxies for that goal and pursue various proxies. For example, it might be useful in order to make human flourishing on Earth everlasting to have an internal optimization loop or some kind of inner learning loop, which is separate from what the outer training is doing. And have that inner optimization loop look for proxy rewards and optimize those. So this is one of the ideas that people have put forward as systems that might emerge inside large, capable AI systems. So others would be power seeking as an instrumental goal, which is helpful for achieving many goals. Okay, so I'll put here inner optimization. And we've talked about in-context learning in this seminar series, which is plausibly something a little bit like that. The key example is, of course, the outer optimization loop of evolution and the inner optimization loop of our in-context learning, if you like, where the context is our life, we are able to learn in a way that isn't tied directly to changing the distribution of alleles in our population. And that may lead to strange goals. Goals that are unanticipated from the point of view of whoever controls the outer optimization loop. So evolution isn't a directed process as far as we can tell, but suppose it was under the control of some entities, and they're aiming at something, and they're quite surprised when they dip in every billion years or so to find that we are here busily optimizing some other goals that have nothing to do, nothing obviously to do with what they wanted when they set up evolution, and may even be orthogonal to what they wanted. The obvious example is contraception. Okay. Anybody want to add anything here in this crash course? So I hope you can see that. That's a sort of, not sure if informal is the right word, unofficial alignment plan from DeepMind that was presented recently at Cerimats by Victoria Krakovna. I think it's like unofficial in the sense that, I don't know, it hasn't been centrally endorsed or something. But anyway, this is coming out of the alignment team inside DeepMind. So the reason I'm putting this up here, I'll put up another slide from this talk of theirs. Partly it's a transparent appeal to authority, right? So I'm going to be talking about some things that, as it turns out, are also mentioned in these slides. But I also want to highlight that some of the people the closest to what's going on have opinions like this. Not many more fundamental innovations needed for AGI. Now, you might disagree that all we need is more large transformers and some more RLHF. Maybe that's not the case, but there are serious people with serious resources and very close to the problem who think this is a pressing issue, right? I don't know if there's anything about these last 2 points I want to read. Yeah, I suppose this is just related to what I was saying, this instrumental convergence or unanticipated emergent properties of these systems being potentially the source of some of the risk. Okay. So that's alignment. It's a serious problem. People are taking it seriously, perhaps not seriously enough. What's it got to do with us? Us being the SLT seminar. Well, it's kind of hilarious in a way, right? So here's SLT in 2023. We have talks about one-layer 10H networks. And then we're very impressed with ourselves when we can compute RLCTs. And here's deep learning in 2023, and we're talking about, well, a 500 billion parameter transformer model is kind of, par for the course, maybe even not that big. Well, there's a slight gap here. All right. Okay, so if SLT is our best hope for taming the beast, maybe like something really dramatic needs to happen. But I say not necessarily. Okay, and the analogy I want to make is I'm going to draw a little cartoon here. So here's logic or language. So we invented logic, and then soon after, it led into the development of the first stored program computers and programming and computer science, and then computer science developed into the science of designing, building, and training large neural networks. And somehow this is it's kind of like a continuum where, you can look inside the code of PyTorch that's training a large transformer, and it's all just code. But of course, once it sort of reaches a certain density and there's all these parameters in there, you don't understand what they're doing. It stops being code in some sense and becomes a different kind of thing. It's kind of like an event horizon of comprehensibility, which the system disappears behind. And then it's sort of a rather different class of object, right? So up here, the coloring is meant to indicate somehow its distance from our ability to comprehend it. There's some kind of transition here where actually we're no longer able to inspect the underlying code and infer much at all. The architecture of a transformer doesn't tell you squat about what it's doing, really. Now that might seem like an insurmountable problem, but let's note that logic and language isn't the bottom of this stack, right? There was a similarly incomprehensible large system sitting underneath this layer. You could go below brains, I guess, down into chemistry and then physics or whatever you like. But there's this funny transition where, despite our brains being something we don't really understand, nonetheless, language and logic have a different kind of character, and then up the stack goes. So I'm going to call this getting lucky, like for interpretability, I guess. Now, logic was invented, I suppose you could say, or discovered, and its original purpose, as stated by Aristotle, was to understand the patterns in human argumentation. Right? You observe people out there, they're spitting out words, they're talking about things in the world, and some deductions are true and some are false. Can you figure out a pattern which explains which deductions are true and which are false? Well, not always, right? Sometimes it depends on contextual knowledge. You just have to know the facts about the world that are being discussed. But there are some patterns which you can look at and use to determine whether or not an argument will be accepted or not, which are invariant under changing the context, changing the topic, changing the objects involved. And that's roughly speaking what logic is. So Aristotle noticed these patterns, wrote them down, and then, maybe 1,000 years later, more, this eventually developed into what we now call modern logic, and then code, and then neural networks. And partly what we're discussing in the context of today's talk is getting lucky again. Right, is there some emergent logic or language which can be used to organize and understand what's happening, at least some of what's happening inside neural networks? And that doesn't necessarily have to look like the original logic, but whatever it is that we're going to use to inspect the machine and understand what it's doing well enough to make it safe will have the character of the way logic organizes our understanding of what humans are talking about and the aspects of their reasoning that is correct or not. Okay. Yeah, maybe I'll just... Okay, so the way I'm personally thinking about alignment at this point is in the vein of being prepared to get lucky. I don't know. I don't know if there is such a thing up here. I don't know if interpretability in any meaningful way is possible. I'll go through some examples. That's the middle third of this talk. Over the years, where people have looked inside neural networks and have a pretty good story about what's going on. So it's not accurate to say they're pure black boxes. That's too pessimistic. Whether or not we can interpret what's going on sufficiently to succeed at alignment is, of course, an open question, and that's why it's a very concerning problem. I don't know that it's going to work, any particular line of investigation, let alone the one I'm going to sketch based on SLT. But it would be really stupid if it does work and we didn't try, and then we're all paperclips, and as semi-sentient paperclips, we're informed that if we only just tried a little bit, it would have been fine, but we were just like too lazy to do it. So I view this line of investigation of alignment based on SLT in the vein of being prepared in case we are lucky. Okay, so now I'm going to talk a bit about examples of interpretability. Any questions or comments so far? Okay, I'll put up the first example. Oh, actually, this... I don't know how many of you have seen Evangelion. So this is the image that comes to mind when I think about interpretability of neural networks. So Evangelion is an anime, very popular. You may have heard of it. In that anime, there's a futuristic city, Tokyo 3, which is governed by 3 AI systems that are sort of linked in some way. And they're ultimately based on uploading some consciousness, or at least that's the germ of each of the AIs. And at various points in the story, something goes wrong. For example, some entity is trying to hack into one of these AIs and set off a self-destruct mechanism. And one of the characters crawls inside this brain-like arrangement of metal pipes, which is covered with all these post-it notes. And these, I think, if I recall correctly, contain various hacks and backdoors that you can use to get the system to do various things. So this is sort of what the state of interpretability looks like, I guess. It's largely inscrutable system, some parts with kind of scrawled notes about something or other that works a little bit like this. But that story does show you that, those hacks actually work to save the main characters. So maybe that's not a bad thing to aim at. Okay, so the first paper I want to show you is a DeepMind paper from I think that's pretty hard to read unless you click on it. Maybe even then it's hard to read. So this is human-level performance in first-person multiplayer games with population-based deep reinforcement learning. It's from 2018. Maybe I'll just put the title up on the previous board. Otherwise known as the CTF paper, Capture the Flag paper. So this is by group at DeepMind. Yeah, that's easy to read. Okay, so what is this paper? This is the interpretability part, but I'll tell you a little bit about what the paper is doing before I tell you about this. Okay, so in this paper, there's a two-player game. There's a multiplayer game with two teams. It's based on Quake 3 Arena Capture the Flag. So there's two teams. There's a flag in each base. To score, you have to go to the opponent's base, pick up their flag, and take it back to your base and touch it with your flag. So if your flag is missing, you can't score. Okay, so they train a population of DeepRL-based agents to play this game, and they succeed in getting good at it. I think probably they're better than humans, and they can also play alongside humans. Okay, so what are we looking at? So the brain-looking thing in the middle here. This is the dots represent projections into 2 dimensions of a high-dimensional vector. So it's a TSNE embedding of the agent state. So the agent has some neural network as its mind. It's making observations of pixels, right? It sees a 3D environment via the same way we would. It processes that and then decides what to do. And the state of the agent is some high-dimensional vector, and it's projected in a way that separates out the projections into clusters. And they're here colored by different combinations. So, for example, you can see, I hope, up here, it says agent flag at base and opponent flag at base and not respawning and agent in home base. So that's a true, those are ground states of the world, things that can be true or false about the agent. And it's observed that the agent state is often in this cluster up here when that combination of states is true. All right. So over here, you can see that they found single neurons, which their activation correlates well with these different observables about the world. The flag status of your team and the opponent's team, whether or not you're respawning. I don't know what agent location means exactly. I guess it's whether you're in the home base or opponent's base. Yeah. Okay, so there are single neurons which you can look at to basically read off what's happening in the world. So obviously the agent sort of knows about these high-level observables about the world. Keep in mind that the agent just sees pixels, right? So it's trained based on just seeing pixels, just a bunch of numbers in a row, and it has to discover these high-level observables from that data. All right. I'm going to think about what else I want to say about this particular paper. Any questions? Yeah, maybe I'll read this part. We hypothesized that trained agents of such high skill have learned a rich representation of the game. To investigate this, we extracted ground truth state from the game engine at each point in time, in terms of 200 binary features, such as do I have the flag, did I see my teammate recently, will I be in the opponent's base soon. We say that the agent has knowledge of a given feature if logistic regression on the internal state of the agent accurately models the feature. In this sense, the internal representation of the agent was found to encode a wide variety of knowledge about the game situation. All right. So this introduces a standard way of telling if knowledge is in a neural network. You take the agent, that's a fixed neural network, you're not changing those weights anymore. And then you train a second neural network, which is a very small network in this case. So it's logistic regression, not a neural network, but it might be a very small neural network, some kind of model which has its own parameters. And you train that on the mapping to learn the mapping from agent state, so this internal vector of states, this, so the activations. So the agent is in a situation which has these 200 things, true or false. It sees some observations. It has some internal state. That's a bunch of numbers. And you want to map those numbers to those true or false values. Now, if you can do that mapping, if you can learn that mapping with a small network which has very few of its own weights, then that's the sense in which this paper, and it's a standard notion in the literature, you would say that those observations are known to the network, or they are represented inside the agent, if you can reproduce that information with a shallow network. Okay, so that's kind of a standard means of probing. These are called probes. Linear probes, if it's a one layer, just a linear projection, or often they're just one hidden layer neural networks. Okay, so in this case from 2018, these probes indicate that the agent is aware of many of these high-level observables about the world. Interestingly, in this paper, I didn't notice this in any of the follow-up work. I think this whole line of deep RL agent investigation kind of ended with alpha star, and they didn't do this kind of analysis with alpha star as far as I remember. But in this paper, they had an automated system of discovering high-level behaviors. So like following a teammate or opponent base camping, home base defense. They had an automated pipeline for discovering these kinds of discrete behaviors from the data and then sort of seeing where they emerge during training. I found that very interesting at the time. So I'm going to put up one more graphic from this paper.
Sorry, Dan, do you mean did they like pick, follow a teammate as something they wanted to look at, or they discovered that as a feature?
Yeah, they discovered that behavior. I don't remember exactly, so I'll read you the passage. It says, "We developed an unsupervised method to automatically discover and quantitatively characterize temporally extended behavior patterns inspired by models of mouse behavior, which groups short gameplay sequences into behavioral clusters. These discovered behaviors included well-known tactics observed in human play, such as waiting in the opponent's base for a flag to reappear, base camping, and so on." So yeah, they claim it was completely automated, which is quite interesting.
Cool.
Okay, I think that's all I have from that paper. Okay, so I'm going to move on to a bit of Bertology. So if there's any further comments or questions about this paper, now's the time. Okay, so we're going to move over to the next set of boards, so please follow me. So this paper is Emergent Linguistic Structure in Artificial Neural Networks Trained by Self-Supervision by Christopher Manning, Kevin Clark, John Hewitt, Urvashi Khandelwal, and Omer Levy. This is a group at Stanford. This is representative of a whole genre of research that was taking place around this time. This was published in 2020 in PNAS. think it kind of died out a bit, or at least I stopped paying attention to it, but there was a very vibrant field for 2 years or so, maybe 3 years, called Bertology. So BERT was a transformer model. Prior to GPT's ascendance, was kind of the hot thing in natural language processing. It's a bit different to the particulars of GPT that we've looked at, in the sense that it doesn't predict the next token, but rather sort of tokens in the middle of a sequence of tokens. But all that's a bit irrelevant for our current purposes. So just think of this as being a system like GPT. So it's trained on language, and then so you can ask the following questions. If a transformer can become very good at predicting the next token in a sentence, it must understand grammar, right? It must understand syntactic structure of sentences, you might think, for some meaning of the word understand. Well, for what meaning of the word understand? What do we think we might find as evidence for the idea that the network understands the structure of a sentence? Okay, so you can do science and look at what kind of things are represented. So, transformers have heads. We haven't really talked much about that, but you could think about a head as being an independent means of attending to tokens. So each head attends to tokens in a sentence in perhaps a different way. And you can see here 6 groups of heads. So heads, head 8 to 10, head 8 to 11. Oh, they're not disjoint, I'm now noticing. Okay, that's strange. Oh no, maybe it's 8-10. So layer 8, the 10th head. I think that's probably what's going on. Anyway, so there are heads here, and they do different things. So it's pointing out that some of the things that some of these heads do sort of make sense from the point of view of linguistics. So I don't know what half of these mean. I guess I know what a preposition is. So prepositions most attend to their objects 76.3% of the time. And you can see some representation of that attention. And then there's various other ideas here. So you can take ideas from linguistics and then go look to see how well various heads seem to correlate with that concept from linguistics, the concept being a predicate that would say 2 words in a sentence are related by this concept or not. For example, a preposition attending to its object would be one of these predicates that would be true or false of a given pair. Okay, and maybe you find some evidence that some heads seem to know about some of those properties. Now that's kind of the transformer analog of noticing a neuron in the agent that we were just looking at in the previous paper that knows about a given predicate about the world, whether the flag is in your base or not. Right? The neurons in a transformer, those are the entities. You don't really expect the representation of an entity to be easily interpretable, but we'll talk about that in a moment. But people notice that these heads seem to have sometimes interpretable content. Okay, you could be skeptical and say, yeah, this is just cherry picking. There's 6 heads here out of gazillions, and these 6, maybe even those, you have to squint a bit to believe they really are about this particular linguistic concept. What about the rest of them? If they just look like garbage, is this really scientifically valid? Yeah, and I would endorse all that skepticism. So, Bertology didn't amount to much, it seems. It was a huge industry of churning out papers, and as far as I'm aware, there wasn't much of a conclusion from all of it. Suggestive, I think, in this case. What I find a bit more convincing is this second example from this paper, which was testing to see if syntax trees were represented. Okay. I'll have to look at the paper to get the story of what's interesting about this sentence straight. Just give me a moment. Okay. Models, I'm reading from the paper now. Models trained to predict words, such as BERT, receive just a list of words as their input and do not explicitly represent syntax. Are they nevertheless able to learn the hierarchical structure of language? Which we think is there, I guess you could say. One approach to investigating this question is through examining the model's prediction in syntax-dependent scenarios, meaning to make a prediction of the next token, you have to understand certain confusions or avoid certain confusions that might be possible if you're not familiar with the syntax. So for example, performing English subject-verb agreement requires an understanding of hierarchical structure. In the sentence, the chef is here. Okay, this is different to this example. Let's see if I can find this particular example. Well, I think it's kind of clear anyway. So if you look at the sentence, is it the chef who was out of food, or was the store out of food? The chef who ran to the store was out of food. So you understand, reading that out of food refers to the chef, right? Even though store is closer. And this is something that people make mistakes on. They tend to associate whatever substructures in the sentence with things that are closer. Okay, so you could say that you kind of need to understand that who ran to the store is something that's attached to the chef, and the overall content is somehow chef was out of food, and then who ran to the store is just some extra information. Okay. All right. So, how would you test whether this structure, this tree, was represented in the network? Well, along the lines of what we just discussed, you might think to yourself, well, I'll train a probe which will look at the activations of the transformer when it's processing this sentence, and then I'll see if that small network can predict this tree. And then you think to yourself, well, what does it mean to predict a tree? That's a little bit tricky. The idea in this paper was to think about a tree as a metric. So you can define a tree in terms of the path length between any pair of vertices in the tree. Okay, so you just have to predict a metric on that set of words. And then you can read a metric off from just embedding the words as vectors in a vector space just by taking the distance between them. Okay, so then you might have the idea that let me train a linear transformation that will take the representation of the words as they're processed by the transformer. So just to draw the standard transformer picture that we've been drawing a few times. Okay, they're the entities that represent the words. So this is chef and so on, just for the sake of argument, making tokens equal to words. Okay, so there's attention that gets processed, Then at some layer here, you grab this vector and that vector. Those are the vector representations of the words in the sentence. Let's call them V1, V2. You take V1, V2, how many words are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You take that collection of vectors in R to the D, and then you take a minimum spanning graph. Spanning tree. That is, you view those vectors as a complete graph where the edges are labeled by the distances between them, the L2 distances, and then you find in that complete labeled graph a minimum spanning tree. And then, well, sorry, I lie. You don't just take those vectors, you're trying to learn a linear map. Okay, so you ask the question, is there a way of linearly transforming those vectors such that the minimum spanning tree of BV1 through BV11 agrees with the syntax tree that a human linguist would associate to that sentence? So that is a loss function on the B, right? You have some labeled data set of sentences with syntax trees. You see if you can learn a B such that this works. And if you can, by virtue of B being a very small network, if you like, so a very small amount of data, you say that that syntax tree is represented in the network, and they show this works. So they can train a B, which works very well. And I find this actually convincing in a way that the sort of Bertology of the heads is kind of a bit of voodoo. Okay, so that's some evidence that the syntax tree has been inferred from the model just trying to predict the next token over the corpus. Okay, so that's my second example of interpretability. Any questions? All right. So I have one more example. Okay, so why am I talking about these examples? Well, I want you to have the idea that it's not impossible to understand some of what's happening inside a neural network. It's not a pure black box. It's not hopeless to attempt to develop a science of interpretability. So that's the point of these examples. So the first two were illustrating that it is possible to look inside and see individual neurons or individual heads which have some meaning. It's also possible to probe these networks by training small classifiers in order to discover whether certain knowledge is present or not inside a network. Notice in both of the cases of probes, so probing for game state in the first-person shooter example and probing for sentence syntax trees in the Bertology example, you had to know what you were looking for, right? You had to know some relevant game state that you were going to test whether it's present or not, and you had to already have some idea of what a syntax tree was. That's because you need to have a training objective to train your probe, right? So the probe idea of understanding what's happening inside a neural network depends to some degree on already having pre-existing knowledge of some conceptual content which you could try and see whether it's represented or not. Okay, so that's something to note. So my third example is it's from one of my papers. That's not the title. So it's called Logic and the Two-Simplicial Transformer. So this was in ICLR in 2020. And the point of this third example is to introduce the role of phase transitions. Okay, so I want you to sort of see that there's an existing literature looking at content of individual neurons, probes, and also phase transitions. And this obviously is just a paper I know well. There are plenty of other papers that illustrate the same point. Okay, so I'll briefly talk you through what this was training a DeepRL agent to play a game. The game is shown on the left-hand board here. You are the dark gray square. You move around the game board. These colored, well, everything that's light gray is the floor. And you can move on it. And these colored boxes are keys. I noticed on YouTube that my son found a YouTuber playing a game that is basically this game. So you can actually find this on the Steam store, more or less, if you want. So how does this game work? Well, you pick up the keys. In this case, it's a light green key. This is a locked box. It accepts a key of this color, and if you open the box, you get a key of this color. All right. So the strategy here is to pick up the light green key, get an orange key, go and get another orange key. That'll give you a dark green key. Your aim is to get the white. And to pick up the white, you need two keys. You need a dark green key. You also need a dark blue key. How are you going to get a dark blue key? Well, you're going to go pick up the magenta key. You're going to use that to get a purple key. You're going to spend the purple key to get the blue key. Then you've got both the keys you need and you win. Okay, so I hope you can see how you might fail to win. Are you smarter than my DeepRL agent? Or at least as smart? How could you fail? So you could spend the orange key to get the purple key. Right, so notice the only way to get the dark orange key is to get the the only way to get the dark green key is to get the orange key. So you have to use the orange key to get the bright green key. You have two ways of getting the purple key. You can use the magenta key, which would be this edge here, or you can use the orange key. Okay, but if you use the orange key, then you've given up your ability to get this, follow this path. All right, so it's not really important the structure of these puzzles, but I want you to give you some idea of the fact that there's logical structure in this puzzle, and it's actually conjunction. Okay, so that's the structure of the environment. The environment the DeepRL agent is existing in has this logical structure, and in order to perform well, it needs to infer this logical structure. And you can see on the right-hand side here the graphs of that happening. Okay, so you can ignore this because this was our baseline. So you can see here that there's some kind of rapid transition in the probability that the agent solves a given class of problems of this type. Okay, so the two rows here, just excuse me for one moment, I just have to fix something. Right, I'm back. Okay, so you can see on the left-hand side here that this indicates a sub-distribution, or like a subset of the training set, or subset of puzzles. Right, so the set of all puzzles, well, puzzles are parameterized by these graphs, right? And you can think about the configuration of which keys open which locks as a graph. Different graphs give different puzzles. Some puzzles are harder than others. Okay, so there's 3, 3, 5 puzzles, which look like the top row there, but with different colors, right? You can imagine swapping out purple for blue. That would be a different puzzle. It looks different, but it's got the same logical content. Okay, so you imagine the subset of puzzles which have the configuration of the top one just with different colors. And similarly, there's a subset of puzzles down here. And you can measure how well the agent does across, this is kind of time, across time on the puzzles of that kind. And you'll see graphs like this, where the agent undergoes some kind of phase transition. You might think it's not conclusive evidence of a phase transition, but a rapid change in its ability to perform this given subset of the puzzles. All right, and this is a typical thing that you see in training deep RL agents. But I want to point out something, which is, I don't have the graph here, but the overall performance. So if you just track the number of puzzles solved, like the probability it's going to succeed at solving a puzzle over the course of training. Of course, it goes up and to the right, but it's kind of much more gradual. It looks something like that. But when you peek into various subsets of the training distribution, so various subsets of puzzles, in those subsets you will often see phase transitions. Okay, so that's another important concept. The fact that the overall performance might look smooth, but the overall performance is maybe an average over many different clusters of tasks or subtasks within that, which do not have the same smooth behavior over time, but may have phase transitions.
Dan, what's a relational agent?
Yeah, this is just a... we had a baseline, so this was some agent that has some fancy new feature in it. This was our agent.
I see.
And this was just a transformer-based agent.
I see. Cool. Thanks.
Yeah. So our selling point was that our agent, because it somehow had this better architecture, somehow got these harder puzzles in a way that the transformer-based agent didn't. I don't care whether you believe that or not. It's not important. But so yeah, you can just. The takeaway here is just that there is an agent and it undergoes phase transitions on subsets of the training set. All right, so those are my three examples of interpretability. I'm not saying that you can understand what's going on inside this agent. I did try a little bit. I don't claim that there's anything much to say there. I don't understand what the heads are doing or what the attention really is doing inside these agents. But you can look at the training and kind of see that, it got something, roughly speaking, at a given point. All right. So now I want to come back to the talk from DeepMind that I mentioned. So this is their approach to alignment, and I want to make a few comments on that, and then I'll finish by briefly talking through, well, maybe I won't even have time to talk about the alignment plan that's on the webpage, but I'll give some motivation for it at least. Okay, so the things I want you to see here are these two lines. So their overall idea for how to align sophisticated AI systems is that it will be something that they do during the training process. I'll reproduce one of their graphics myself. So their idea is that you have a space of possible models. You start somewhere, there's a training process, and you need to detect if your training process is heading towards this danger zone. So the danger zone would be a misaligned AI that is going to behave like the monkey's paw. And you detect that you're heading in that direction and you stop and you go in a better direction. and then, oh no, you stop again, and then you keep going, right? So this relies on, well, there's two things to notice about this, right? Fundamentally, you do it at training time. So while the model is becoming more capable, during that process, you are paying attention to it. You are trying to understand how it works and what it does, and whether it's potentially dangerous. And if you do detect that, you change what you're doing. You go in a different training direction. So this plan relies very critically on being able to understand, being able to inspect the machine, right? Interpretability. So as they say here, mechanistic interpretability is a key ingredient. And also predicting phase transitions. They mentioned grokking here. I don't know. I think grokking is kind of like overhyped. But anyway, so people have noticed in GPT and many other systems that just as in this example I was showing you, while the overall loss function of GPT smoothly decreases, if you look at subsets of the training distribution, for example, arithmetic problems or French to English translation, the losses for those or their accuracy do not have the same kind of gradual change. There are often phase transitions. Okay, so this is also something that is put forward as being something to pay attention to during the training process in order to hopefully arrive at the aligned system. Okay, so now I want to say something about SLT. Any questions about this slide? Well, so as Watanabe says, knowledge to be discovered from examples corresponds to a singularity. But I mean, you can be too naive about that, right? It's not necessarily that means that everything that there is to say, like all the structure in the knowledge, is reflected by structure of the singularity. Now, I've shown you 3 examples, and each of those examples has structure, right? The deep RL agent is just perceiving pixels, but those pixels have structure, and that structure is the rules of the game, and the rules of the game include bases and flags. The sentences have structure, that's the syntax tree. The box world game has structure, and that's the logical structure of the relationship between keys and locks. Now, if you train a model on those environments, that model will be singular, and it will have singularities. Okay, and we know that some properties of the learning process or the model, like generalization error, will be reflected by geometry of that singularity. But that does not necessarily imply that the structure we see in the training distribution, in the true distribution, in the environment, is necessarily reflected by structure of the singularity. Right? That's not necessarily true. So that's the question. So is structure, for a very broad meaning of structure, is structure of the knowledge? Maybe I should phrase it differently. Does structure of knowledge correspond to structure of singularities? If the answer is yes, then we can try and use methods of SLT to understand that structure empirically. There's a question of how to make it sufficiently scalable and so on, and I'll, I guess, address that on a different occasion. It's in that plan document. But then we can hope to apply methods of SLT to learn the structure of singularities and from that infer something about the structure of knowledge. But it hinges on the answer to this being yes. Okay, and this is an empirical question. I don't claim to know the answer yet. I think it's important to investigate, and there's plenty of ways to start trying to do that. What I want to communicate is my reason for suspecting it's true. Okay, so I don't think it automatically follows just from the general theory, but I can give you some examples, or an example where it's where I know it's true. Okay, so this is the following comments are based on Tom Waring's thesis, which is geometric perspectives on program synthesis and semantics. Also on a preprint by James Clift, myself, and James Walbridge on a similar topic. So this is from 2021. Well, the reason to be somewhat skeptical of the answer to this question is yes, is that, well, the singularity is about the degeneracy in the parameter. The more equations you need to cut out the set of true parameters, the sort of higher the normal number of normal directions. So it's got to do with degeneracy in the parameter rather than structure, right? At least that's maybe how it seems. So So what Tom does in his thesis is develop a dictionary or a translation between Turing machines, or lambda terms, by coming up with a SLT learning machine, an SLT triple associated to any Turing machine. You can identify the Turing machine with a singularity, and that has the following property. So the structure of the proof, the structure of the Turing machine, and I'll give you some indication of what that means in a moment. You can see how that corresponds to degeneracy, and how that degeneracy becomes symmetry of the singularity. Literally, and it's symmetric under just the action of a symmetric group that interchanges coordinates. Okay, so that's a clear way in which, at least in this example, you can see exactly how structure on this side corresponds to structure on that side. And I'll give you a bit of an idea of what kind of structure I'm talking about. I apologize. This example requires a bit of background, but maybe, hopefully, it gives you a bit of the idea, even if you're not familiar with this story. So this is a picture of a lambda term, or a sequent calculus proof tree. You can think of it as a program. It's actually it's the number 2 in some prototypical functional programming language called lambda calculus. Doesn't really matter. What I want you to notice is the colors. Okay, so there's a sense in which, and you can make this very precise in linear logic, the information content of a program lies in the pattern of equality of occurrences of variables. So this program here is I can't write down the church numeral 2 now after writing this hundreds of times. No, the other way around, I think. Yeah. Yeah. There are two y's. That's the point I'm making. So the reason that it's a church numeral 2 is there are two occurrences of the variable y. And the way this proof tree works is you start off with two different variables, y and y prime, and then they're set equal to a common y. So basically there's a step here where the program actually looks like I'm given a y and a y prime, and I apply, I don't know, y prime to y to x. So there's a y and a y prime, and then by a step called contraction, y is set equal to y prime. The point is that somehow the entirety of how that lambda term computes is tied up in introducing sort of many distinct variables and then identifying some of them in some pattern. And that degeneracy, that identification, that equation, y equals y prime, ends up contributing to the symmetry of the singularity on the left-hand board. And that's not the entirety of its structure, but you can see, if you're familiar with this whole story, how the structure of the lambda term gets translated into the structure of that singularity, at least some of its structure. So this is at least one example where the answer is yes. The knowledge in this case, the solution to the synthesis problem, is this Turing machine, and the structure of that knowledge is as a clear translation into the structure of the singularity. So on that basis, I'm, I guess, hopeful that some of the other examples we were just discussing, that if we were to be able to understand the singularities that are associated to them, we would also see, for example, those syntax trees might be reflected in structure of the singularities of those models. Okay, and that's the foundation for hoping that we can move forward with using analysis of singularities to help with interpretability. I think I'm going to have to stop there, given that it's nearly the end of the time, so I apologize for not actually getting to the content of the alignment plan. But I think this is now a good introduction to some of the reasons why I think it's feasible. Questions? Okay. Yeah, I don't know how much of the structure of lambda terms can be inferred from the singularity. I guess I think all of it, but I don't know how to prove that. I don't expect to find the exact structure of lambda terms in larger neural networks or anything like that, but understanding how the logical structure in this kind of example translates into structure of singularities is, I think, a useful guide to trying to figure out what logical structure looks like when you go looking inside neural networks. What kind of geometry is associated to that? Maybe there's a kind of generic answer. Any quick questions about any of the earlier examples? I posted the papers on the Discord, so I encourage you to take a look at those. We've talked earlier in the seminar about the interpretability work, mechanistic interpretability work at Anthropic and elsewhere, so the toy models, the superposition paper. So there's an induction heads paper out of that group as well, which is also very interesting. And understanding the geometry associated to those seems like a very good starting point.